Hey, also, here's a few quick calculations we can do with ease. Let's say we've got water and the pressure, it's atmospheric pressure. We want to figure out the temperature at which water boils. So I can do this with ease. I can say T, let's just call it T1, and we'll call it temperature, and we'll use water as the material. And let's say, I think I said the pressure is 101.3 kilopascal. And I want to know, let's say the quality is equal to 0. It means it's saturated water. It's right about to boil. So here's the query. You could look this up in the saturated water table if you wanted to. Let's check the variables, and the temperature, I expect units of degrees C, and I'll click OK. So this is telling me what is the temperature at which water would occur when it's saturated, and I'll hit the calculator button, or I can push F2 on my keyboard as a hotkey, and indeed it says the temperature of water will boil at 100 degrees C at 1 atmosphere. And if I want to, I can say let's call it P1. P1 is 101.3 kilopascal. We'll put it up there. And in here, I'll just say P is equal to P1. And this ought to return the same thing. I'll click Variables again, this button, or I'll click F9 to bring it open. And P1 I expect it to be in kilopascal, and that looks okay. Push F2 to run it, and so again, the same results. P1 I said 101.3, and T1's 100. Let's say I want to know the specific volume at which this occurs. Let's say V, we'll call it V hat 1, and I'll use the volume function, and I'll use the exact, I'll just copy and paste this, and I'll hit F9, check the units on it. V hat 1, I expect cubic meters per kilogram is the appropriate units. I'll click OK, I'll push F2, and what this is telling me is that the specific volume of water is 0.001 cubic meters per kilogram. Let's say I also want to know, the density. I'll say density, rho, Greek symbol rho is what we usually use for density, and again I'll just use the same conditions, paste this into here. F9, let's check the units, density, kilograms per meter cubed, and click OK. The density is the inverse of the specific volume, and I come up with a density of just shy of 1,000 kilograms per cubic meter, which is true for water. So let's get rid of that density. We don't quite need it right now. And let's say V hat 1 is for saturated water. Let's say V hat, or here I'll call this V hat L. Commonly you use L for liquid, and V hat vapor. And this will be, instead of saturated liquid, let's call it saturated vapor, and X is equal to 1 in this case. So V hat L and V hat V, or V hat, let's use V hat G. Now here, actually, to be consistent, let's use V hat F for the fluid, or the liquid, and G for gas, or the vapor, and this is the notation the book will use. And hit F9 to check the units on it. I expect, for both of these, cubic meters per kilogram. And I'll click OK, and F2 to run it, and what I come up with, V hat fluid, so 0.001 cubic meters per kilogram, and if it was a vapor, I get 1.67 cubic meters per kilogram. So let's we'll just get rid of all of, I guess, this temperature. I won't use it for right now. What would happen if I said, I know the pressure and the specific volume. Let's say the specific volume is 0.5 cubic meters per kilogram, and that specific volume V1 is going to be somewhere between the specific volume of the fluid and the gas, meaning that it'll be in the two-phase region. And I want to know the quality of that. So let's say I want to find X1, and I'll use the quality, and again I'll just copy here. No, we want to find the quality, so I'll say water, and P is equal to P1. And now I want to say the volume, V, is equal to V1, the specific volume. And this will return, if I check the units, looks like everything's okay, quality is dimensionless, I'll click OK, and click F2. And that's telling me, under these conditions, with a specific volume of 0.5 cubic meters per kilogram, and the pressure of 101 of atmospheric pressure, that means that the quality is equal to 30%. Let's say you were wondering, is it a two-phase liquid, is it supercooled, is it subcooled, or is it a superheated vapor? there's a function, let's call it phase, we'll call it phase, this is the variable. I need to put a $ after it because it's going to be what's called a string variable, or a letter of characters. And the function is phase $, and I want to figure out the phase of the component, and I'll copy these and I'll paste it. And if I hit run, what it's telling me, the phase in this case is saturated water. It's in the two-phase envelope, in other words. So let's explore this a little bit more. I'm going to get rid of all this other stuff. We don't really need it to explore this. If I took water at a given pressure and I had a small specific volume, and if the specific volume is really small, it would be all liquid. As it gets bigger, some of the liquid evaporates. As it gets even larger, we can say, let's say the specific volume is 1.5 cubic meters per kilogram, and I run that, and it's still saturated. As it continues to expand, I can say 1.6 cubic meters per kilogram, and if I run this, it's still saturated. And right when I hit, under these conditions, as it gets a little bit bigger, it goes from saturated to superheated. Now, in a two-phase envelope, you'd see this moving into the superheated region outside of the two-phase envelope. And one of your homework problems in the table, it's saying T is equal, let's say 150 degrees C, and the pressure is equal to 250 kilopascal. So let's call this T1, and P is equal to P1. So that means if I want to know the phase, let's call it phase 4 is a variable, and the function is phase, and we want to work with water. And you can either spell out the word water or the word steam, you'll get the same thing. And let's say it's T is equal to T1 and P is equal to P1. And what this ought to show us is the phase that the water exists in under these conditions. And what we find is that it's indeed in the superheated region, and it's superheated water. Let's say I wanted to know the internal energy, and let's call this, we'd call it U4, for example. The function is called int energy, and again we're going to do water. T is equal to T1, P is equal to P1. And let's check the units on this. And we expect the units to be kilojoules per kilogram. I'll click OK. And then if I run it, click the calculator, this is what I come up with, is U is equal to 2,574 kilojoules per kilogram. I can also do things, let me clear this, I can also do something like, let's say I know T is equal to 1,300 degrees C. And I also know that the internal energy, we'll call this T3, I suppose, and we could call this U3. Use the variable U for internal energy. And I know the internal energy is 4676.1, and the variable is kilojoules per kilogram. And I want to find, let's say I want to find the pressure that water might occur at under these conditions. So I'll say pressure, water, and T is equal to T3. U is equal to U3 for this. And I check the units. I've got pressure. I expect a pressure of kilopascal, so I click OK. And if I run it, I come up with a pressure, in this case, or here, let's use something a little bit more accurate even. The function I can use is called steam, and it's underscore International Association of Properties of Water and Steam, IAPWS. And this will recreate exactly the tables in the back of your book, the saturated, or all the water tables. And if I run that, I come up with a pressure of a little over 7,000 kilopascal. And if you verify this, you can use it, you can look in your book to verify something like this, and you should come up with the same number.